Good water.
Yeah, of course. Hello, Mr. and Mr. Ryan, are you right?
No.
Okay. Okay, so let's look at this. Okay, so we're given this array of integers. We are given this binary integers, okay? Binary, so what's binary?
Using only 2 digits.
Yeah, 0 and 1. So we're given an array of binary integers. We're given an array which contains only 0 or 1s, okay?
Maybe that.
So we want to find out, we want to count how many subarrays. Do you remember the subarray? The difference between subarray and subsequent. Subarrays are continuous.
Like, yeah. Well,
Subsequent is that you can pick, right? You can pick or skip each digit. Subarray, usually when we talk about subarray, we can Bruteforce using O(n) squared, right? Right? Because they, for the subarray, we can pick one index for the left and one index for the right. Okay? And they are n squared choice. This question, we want to count how many subarrays which each neighbor digits are different. Okay, so for example, given this, can you count how many subarrays which every neighbor digits are different? For example, the first one.
1.
Yeah, 0, 1, 1, 1. So there are 4 subarrays. Each one is 1 digit, right? And also.
Wait, so can it be like
0,
0, 1, 1, 1, 1?
No, because 0, 1, 1, 1, right?
Yeah.
These two are the same. We want to find out. We want to.
So it has to be like.
Different, yes. Every single, every neighbor.
So it has to like alternate between.
That's right, yes. It has to be different. Okay. So how many? What's the remaining one? So I just told you that there are 4, right? Which is 0. This is one subarray. 1, 1, 1. So there are 4. Each subarray of size 1 meets such requirement, right? Because it's 1 digit and there's no neighbor, so it
So
counts.
it could be 0 and 1, so it's 5.
Yeah. So that's 5. Yes. Okay.
Oh.
And how about this one? Why is it 10?
Okay, so 1, 0, 1, 0.
1. Okay. 1, 0, 1, 0. There are 4. Okay.
No, I meant like 1, 0, 1, 0 as a whole.
Okay, so 1, 0, 1, 0. So that's 1. Okay. So 4 plus 1, 5.
We have 1, 0.
1, 0.
And there's another 1, 0.
Okay. And?
There's 1, 0, 1.
Okay, so 1 is missing. If it's size 2, 1 is missing. 1, 0, you 1, 0, and 0, 1, right?
Oh yeah.
Okay, and then?
And 1, 0, 1.
1, 0, 1.
And 0, 1, 0.
0, 1, 0. Okay, so that's 2, right? 4 plus 1 plus 3 plus 2 is 10. Okay, you got it right. Okay, so how can we count? So let's repeat. We are given an array of binary digits, 0 and 1. We want to count how many subarrays which contains, which does not contain the same neighbor digits. Okay, so this does not count the empty subarray. Okay, the subarray of size 1 meets such requirement because there's no neighbor. Make sense?
Yeah.
What's your idea? What's your idea? Huh? What's your idea? Can I help you? Okay, come on. Let's focus on this. Okay.
So it's always like the amount of digits in the array, because you can just have a subarray of just 1. So. And if it's just like only 1s or only 0s, then you return like the amount of numbers in the array.
That's not nice.
Oh yeah. If it's
That's
all
not
the same.
nice, Dad.
Okay. Every time I close the door, they want to go out. Right? If they're outside, they want to come in. Okay. So
Then why do you
okay,
close,
so let me
then
get
why do you
this.
close the door?
Okay, let me get this straight. You're saying that if the array contains only one values, then the answer is the number of elements, right?
Yeah.
That's obvious. But if it's
Yeah,
different,
yeah.
how is that?
For example, like if there's only like one different one, like 1, 0, 1, 1, 1, 1, like so you have to build your so you have to first of all you have to count the amount of elements in the array, and then you have to build your like subarrays around that different. Yeah. Like the one before, you know for 1010. Yeah, that's what we're doing. Like you check with a subarray of. We could do Bruteforce, for example. You can.
Yeah, Bruteforce.
For example, you can just check with a subarray with size 1 and then go through the whole list.
And size 2.
Yeah, size 2, size 3, size 4 until you like.
So we can just check different every subarray, right? We can choose subarray. So how can we Bruteforce all the subarray? Easy, yeah? We have a for loop, 2 nested for loops, right? One for the left index, one for the right index, and then we just once we have this subarray, we can just validate to check if it has these different digits for every single neighbors, right? That's obvious. What's the time complexity for that one? If I'm going to write it. Okay, so Bruteforce is O(n) square is to get the Bruteforce, get the subarray, but we still have to check to validate.
O(n) cubed.
Yeah, O(n) cubed. So it's O(n) squared times n, right? Why is that? Look, for example, like
How
if
can you write O(n) cubed?
yeah, it's the same. O(n) cubed. Yeah. So for I in range n, right? For j in range, start with I till the n, right? Start with I till the n.
Column.
Yeah, and then the subarray. So subarray is from S. If this is S from I to J plus 1, right? Up to J, not including J. Up to J plus 1, not including J plus 1. So it's up to J, and we just have to validate this subarray to see if it contains the different neighboring digits. So look, this is O(n) square, and then another O(n) here, so it's O(n) cubed. So this is certainly not the optimum solution. Okay, not the optimum solution. So why this is subarray is O(n) square? So for example, like if
I thought you said it's
yeah, I mean this one O(n) square. How can we interpret
because
this?
before, like I remember you saying that.
Yeah.
That all I remember is that you just look at the fours, like if it says 2 4s.
Yeah. For each for loop, for each I, we need to take. So let's look at this.
That looks like OW, not ON.
Yeah. Okay. Come on. Listen. For each I iterates from 0 to n minus 1. So I needs to take n steps, right? For I step on one step, then the j needs to iterate roughly on n steps. Okay, so it's actually, this is not exactly O(n) square, it's not exactly n square, but it's n squared divided by 2. So actually we drop the constant is O(n) square. Why? For example, like if we want to find out the number of subarrays, so we know that subarray size 1 is a subarray, right? So there are n choice. We want to pick 1. How many choices is this? There are n choice, right? Yeah. So it's Cn1, right? So if the subarray is size 1, so there are n apples. We want to pick 1 apple. So how many choices? Cn1. This is n. Okay.
Yeah.
Okay. So if the subarray contains more than one digit, one digit, so we can pick one index for the left, or pick one index for the right, right? So if for example, if I pick this for the left, pick this for the right, so the subarray is this, right? We can have how many? So it's Cn2, right? So basically there are n apples. We want to pick 2 apples, 1 for the left, 1 for the right. Okay, so this is the subarray, the number of subarray which contain more than one digit. This is the number of subarray which contain only one digit, plus it together. Cn1 is actually 1, right? N apples, picking 1 apple, how many choice? You have 4 bananas. Yeah, n, yeah. N. Cn2, n apples, picking 2 apples. So it's n times n minus 1 divided by 2. So if we add it up together, it's n times n plus 1 divided by 2. Okay, so it's n squared plus n divided by 2. We drop the constant, and this is the trivial part. We drop it, so the time complexity for the subarrays is O(n) squared. This is how we get it. So
Okay.
good. Okay, so I'm going to tell you what's the ultimate solution, right? We can use dynamic programming. If I tell you dpi is the number of the such array ending at index I. If I'm saying dpi is the number of the such subarray which ends at index I. Okay, so what's the answer?
I.
What's the answer? What's the total answer? Is it the answer equals dp, the sum of dpi for I equals 0 to n minus 1, right? So basically this is the number of subarray. That means the requirement which ends the index I. So the answer is that we want to find out that we want to count the number of subarray which ends the index 0, number of subarray which end index 1, etc. Right? Yeah, this is the symbol of sum. Okay? This is the mathematical symbol for sum. Yeah? For example, like 1 plus 2 plus 3 plus till 100. This is 50, 50, right? So we can write it this way. I. Okay? For I equals 0 to I equals 1 to 100. We can write it this way. Okay? Yeah, makes sense? As I said, dpi is the number of such subarray which at index I. Then the answer is that accumulate dpi for I equals 0 to n minus 1. So basically we want to accumulate every subarray at index that ends at index, each index, okay? So now with this, it's simple, right? We just iterate from left to right. We just check if this digit is the same as the previous digit. If this index is the different as the previous index, right? Then dpi equals dpi minus 1 plus 1, right? If this digit is different than the previous digit, we have this, right? Because we just simply have one more subarray. Does it make sense? Look, for example, like 1, 0. Okay, if I'm telling you, look, the next digit is 1. The next digit is 1. This 1 is different than the previous 0, right? So the number of the subarray which ends at least this 1 should be the number of the subarray which ends the previous 0 plus 1, right?
What are you talking about?
Good question. Good question. So what I'm saying is that dpi is the subarray that ends, such subarray which ends at index I. So if this digit is different with the previous digit, then we know dpi equals dpi minus 1 plus 1. So dpi minus 1 is the number of the subarray which ends the previous index plus 1. Because we have one more, right? We have one more.
Okay.
Yeah, okay. So if it's the same, if the previous one is 1, and then now we have 1, then dpi will be 1, right? Because it does not form, right? It does not form any valid subarray with the previous one, right? Because look, this is 1, and dpi must be 1 only. Am I right? Because the previous one, we cannot include the previous one, right? Because if we include it, it will be invalid. Okay, so with that, let me write the code. It should be very simple. Okay, dp answer at the beginning, answer equals 0. dp equals at the beginning 0 times n, right? But dp0 is 1. Okay, because the first one, we start with the first one. For I in range 1 to n, if the numbers I equal numbers I minus 1, if it's the same as the previous one, then dpi should be start with the 1, right? Else dpi should be equals to dpi minus 1 plus 1. And then we need to accumulate answer equal dpi. And then return answer.
Okay.
Okay, let me explain this. Okay, so there's one problem, which is because we start with 1, so we need to put this as 1, because we start with the second number. So the first one, the first digit always is a valid subarray, so we need to start with 1. Okay, so as you can see, right, we iterate over the loop. We just need to accumulate dpi, so we don't need to store the numbers into the dp array. This is on space, right? So we can just use another variable, for example, like size. Okay, so size equals 1. Okay, so if nums I equals nums I minus 1, if it's the same as the previous one, then size is equals 1, because this is the number, size is the number of the subarrays, current subarray, right? If it's different than previous one, then we can accumulate, actually answer plus equals size. Then if it's different than the previous one, then we can put another digit. We can put another digit to the current subarray. So we need to size plus equal 1, right? Okay, so let me use this example, 1, 0, 1, 0, so you know what I'm talking about, okay? Look. Yeah? What's this answer? 10, right? We just found out this is 10, right? Look. Yeah? Okay, so the answer, let me put this answer at the beginning is, we start with the second one, right? Second value here. Answer equals 1, okay? Because we know the first single one is a valid one, right? Valid subarray. And then current size equals 1, okay? So now look, we are at the second digit. Is this the same as the previous one? No, right? It's not the same. It means that the current subarray is 1, 0. The size is 2. So size is 2. The answer must plus equals 2. Okay? Why? Because look, 1, 0, 1, 0 plus 2 equals 3. Okay? Okay? And now, if I move to this one is different than 0, right? This one is different than 0. So we have one more. So size plus equal 1, which is 3. Okay, the answer plus size, which is 6. 3 plus 3 is 6. Why? Because when we have this one, we have how many? We have how many? We have 1, 0, 1, 1, 0, 1. Okay? You get it? Does it make sense? Look.
Okay.
Yeah? Look, when we have this one, how many more subarrays we have? This is different than that. How many more subarrays? We have 1, single 1, 0, 1.
Yeah.
And what else? 1, 0, 1, right? So we plus 3. Okay, now move to the next one. 0 is different than 1, right? So how many more subarray? This is become 4, right? 4. How many subarray? Plus 4, right? Plus 4. So this is 10. Why plus 4? 0, 1, 0, 0, 1, 0, 1, 0, 1, 0. If it's the same, if I put another 0 at the end, if it's the same, then we need to set this size to 1. Because we can't say 0, 0, 0, 0 is invalid. So all the previous one will be invalidated, right? So that's what I said here. If it's the same as the previous one, we can only have 1. We need to set it to size 1. Otherwise, we can accumulate, we can extend the current subarray. Make sense? Okay, so let's look at this. 1, 0, 1, okay? This is the current subarray. What happens if I put a 0 here? How many more subarrays can we get? How many? If this digit is different than the previous one, how many more subarrays we can get? Is it always single, right? We can have the single, right? Yeah? Does it make sense? Yeah?
Yeah.
And what else? 1, 0, right? What else? 0, 1, 0, right? What else? 1, 0, 1, 0, right? Okay? So this bit is dpi minus 1. And this is 1, right? So dpi equals dpi minus 1 plus 1. Okay? Makes sense. If this is different than the previous one, dynamic programming, we are using the previous result. But if it's the same, then all these are invalid, right? If it's the same, I can't use that. I can't put the 1 here, right? Because it's invalid result. So I can't use here. But I can still use this, which is 1, right? So dp, if it's the same, then dpi equals 1, right?
So if 1 before it is the same, then just add 1 and then.
If it's the same, then we can only add 1. If it's different, then we can use the previous one plus 1, right? Yeah. That's time complexities, we're just going through once, so it's O(n). The space complexity O(n) constant if we're using this size, we are not using the array, okay? Yeah, makes sense. That's it for today. Bye bye.
Um,
Bye bye.